about to show you our latest development in our IM mobility software. Here you can use the PNNL preprocessor, as we described in previous tutorials, to generate MZMLs from .ds if you need to convert in that way, from .d Agilent files that are actually data dependent type structures. So you take an LC IM mobility DIA data file, and then PNNL's preprocessor does some deconvolution, generates an DDA, LC DDA-like file, and then, as we discussed in previous tutorials, you can then use that in a two-part process using FluoroMatch IM and a modular script within FluoroMatch IM to generate all the data needed to get both MSMS identifications and IM mobility identifications, which is very exciting. So here's the resulting data. There is a slight interesting artifact here where the mass defect seems to increase across these series. That's something we can look to, but otherwise everything's working wonderful. And so let's pull in, again, there's all these different filters. You can look at some of the other FluoroMatch tutorials to see how these filters, but we'll play with for a little. So A's are either MSMS identifications that are very confident, less than 5% false positives using standard-based rules, or CCS matches. And then there's a bunch of other scores related to either CCS or MSMS. And what the software does is it takes the best score from either. And so when we take A, it's either a CCS match or a nice MSMS match. And now let's go into the number in series, and let's just pull out some of the major series that have a lot of members. And we can show our scores so that we show everything if we want. So unselected also shows everything. And now you can see these nice trends along the MZ drift time and retention time. And you can see also series that fall outside of those trends. So, this would be series 71. So this is an interesting one that's way outside of that trend. And then there's other ones here. And you can use this to zoom in, find in-source fragments, so on and so forth. And so you can really explore this data set going series by series. For example, in this series, you can see quite a bit of isomers, the blue one. So, the nice thing is we can also pull out individual series. And we can look at those as well. Here you can see retention time versus mass to charge and drift time versus mass to charge. And the cool thing here too is that we can pull in any of these three, and we can see it's annotated MSMS spectra. We'll come back to that. But let's look at the EIC's data. Here you can see retention time filtered EIC plots, drift time filtered EIC plots, and retention time filtered mobilograms. And so you can see for these three species, although you would consider them as a single peak, if you just looked at the mobilogram, as you filter by retention time, you can actually see their different CCS values and their separation, even though they are isomers. And there are cases, of course, where there's things that are isolated just in mobility time and not in retention time. And then there's the vice versa case too, as you can see here, where things have some separation in retention time, but not mobiligram time. So, being said, we can also look at the tables and we can sort by score. So let's do that. And there's the score for IM. So if I want all the A's, let's do it this way. And then there's also the score for MS&S. And so we can pull out, let's just pull out the top ranking molecules. So that would be A, B plus, so here we can see one molecule in ion mobility and in MS/MS. And it's this phosphonic acid containing species. And you can see that both the formula in IM and the formula in MS/MS are both the same. MS/MS had a lower score, but was able to use fragment name evidence to give this, whereas ion mobility. If we look at even more of these, let's pull out everything. So here now we can see a number of other cases. So here's a PFSA C3HF7O3S. So that's just a perfluorosulfonic acid. And you can see that it's both an A in the ion mobility and an A with MS/MS. And so you can be even more confident. And we can select that species. And you can see its fragmentation with the SO3F, SO3. And scroll over and see that fragmentation. Also those sulfonic acid related fragments. Now you can also look at some unknowns analysis. So let's unselect all our filters. So now we're going to see everything. So this is going to be kind of crazy. So here's the entire data set. And let's go to an unknown. So 55. And here you can see the nice fragmentation for this unknown. We've got SO3. We have a large number of sulfonic acid related fragments. You can see some kind of isomeric details here. A nice mobilogram. So we could get our CCS out of that. And it's an unknown species, but we do have isotopic information here. And then we have formula matches. So for example, you can see that all the formula matches have sulfur because of this sulfur related peak over here at about 4% compared to just the C13 peak. And so that's some idea. And then you can also see with the fragmentation that it gives you substructures of what that molecule could be. So we do have a pentafluorosulfide potentially because we see the SF5. You can see the different branching. We might even be able to see Yeah, here we go. C13F27SO3. So this looks like it's actually the precursor ion. So it was identified, although at the fragment level, as a C13 sulfonic acid. And we can look over here and you can see that there isn't a correct formula prediction, but it does get the sulfur right, which is what these formula predictions are very good at based on the isotopic pattern. So there's a lot more you can do here. Let's take out this filter. There's just a lot of power you have in this software. Obviously, you could filter by CCS, drift time, all of those dimensions on top. You can also do fragment screening. So let's say if I want everything with a sulfonic acid that's also probably fluorinated, I can do this SO3F. And now all of a sudden you see these different charts. And if I want something that potentially has, we can be a little bit more selective by selecting the end. Now it has to have all three of these. And so there you can see that quite a lot still have SO3, SO3F, and SO2F over here. And so we could select now any one of these fragments. Another way to do the fragment, let's just select one of these. And let's say you're only interested in those that have a high intensity. You can scroll over, and set a pretty high intensity threshold. So these are going to be those most abundant. Or let's just say something that has 1,000 or 10,000 signal might be quite high. And now you can see some of these series pull out that are probably sulfonic acid containing species. And we can go into them and try to find, some of them should. So here's an interesting species. So this is a B+, which looks like it has a bunch of sulfonic acid related fragments, and it does have the ether fragments. So we saw that the structure looked like an ether-related species, and indeed it does have these ether-like fragments. And you can definitely see some isomeric potential behavior going on here, even in the drift time. And here you can see the nice isotopic pattern, structure. And we do have a CCS value, so that also helps confirm this. You could use CCS prediction models to see if this makes sense as far as the CCS goes.